So I think I think everyone knows that we have people from very different backgrounds here. You know, everyone has a little bit, everyone is a bit of a mathematician, or at least a bit of mathematician. Some of us are very much mathematicians. And some of us are more implementers, some of you perhaps, and some of us are more type theorists, and some of us are more category theorists. And this is a talk for mostly category theorists. So, you know, if something is not clear and you have a problem, just lift your hand up, because I do not have to get anywhere terribly much. So, I'm Valeria. I work in the Topos Institute, which I've forgotten to say this morning. And I'm going to talk to you about dialectical categories in the more categorical version. Because I cannot resist, I always put back the mission of Topos. So that's what Topos is about. It's about shaping technology for the public benefit. And we want to do that by advancing science of connection and integration. And as I was saying, 2 weeks ago I talked about AI tools for mathematics. Now I want to talk to you about dialectical categories. So this is very vintage work, not to say extremely old and ancient, because this is all from this technical report from Cambridge, which is my thesis, and it is from, to tell you the truth, 1987, but the technical report is from 1991, when I started working in the computer laboratory, because I did my PhD in pure maths and then moved on to the computer lab, because I wanted to use the kind of category theory that I had learned for things in computing. So what I did at that stage was, hang on, let's see if it works. Yeah, so I wanted to, at that stage, I did a thesis with 4 chapters, one about the category DC, one about the category GC, and 2 special structures on these categories, co-free, monoidal comonad, and a more complicated, so I'm calling it a composite monoidal comonad. And I might not get to this point at all, because there's quite a bit of calculations that have to happen to get there. But, you know, I wanted to convince you that, I've been talking to some of you individually. I have written that board out there the blackboard out there several times, because I wanted to convince you that this, despite being a very old work, it's still kind of a very exciting and interesting work. So these are the new bits that we've been doing. So we have a paper in TCS, Theoretical Computer Science, on dialectical principles via Gödel doctrines, and one on the Journal of Logic and Computation on dialectical logical principles, not only rules. And in 2 weeks, John Weinberg is going to come here, and we're working on this dependent Gödel fibration. And David Trotter was here, the picture is still out there, and with him, and so the work on Gödel doctrines is with him. He is the main author. And we are also working on using this kind of mathematical structure, categorical structures, for applications in computability. And that's a new paper. Let's see if I can get, no. He said not to touch the computer, didn't he? But how can I get rid of this thing? Okay, so far so good. No disasters yet. So as I was saying, we have applications on computability, and this is a new paper that is, okay, not so new in the archive, but it's about to appear in the Logical Methods in Computer Science. And as I mentioned last week, when Mirna Dismonja was here, we also kind of did some work on set theory using this kind of structures. And even more recently, it doesn't look like that because it's from June 22 that we had this AMS, MRC applied category theory, and don't. Nope. Anyone has any ideas on back? So This is going to kill me today, seriously. But so in June 2022, we had this AMC applied category theory, and some of the work, and this works like that. You have a few months kind of meeting people, then you have a week researching with them in some place upstate New York, and then people write papers about that. So 2 of the papers that I'm expecting 4 papers from that, and 2 of the papers have just appeared, one last week in Oxford. Okay, so you might be wondering to yourselves, why Dialectica categories? And Dialectica categories come from the name dialectical interpretation, and was first conceived by Kurt Gödel, and he published it in 1958 in the philosophical journal called Dialectica, and that's why the name is so. Some people find it very annoying, the fact that someone named the interpretation just after the journal, but I don't see any problem with that. And what Gödel did, and I'm pretty sure that you guys know that Gödel kind of vaguely destroyed Hilbert's program, right, showing his incompleteness theorems. So what my understanding of what Gödel is doing with his dialectical interpretation is a way of kind of patching up a little bit and saying, okay, maybe you can't have completeness. As I said, this is going to kill me. Too long, too far. No. I do not know why it went to the end. Okay, I can do that. So his way of patching up the stuff was to say, okay, I can prove the consistence of piano arithmetic because I'm very clever and I have a special trick to show you. And the trick was to say that you can transform any formula. You know, you have to use 2 tricks. First trick is transform a piano arithmetic into Heiting arithmetic. And then second trick, if one can use it, is to translate every formula A of Heiting arithmetic, which is the constructed version of arithmetic, into a formula of this shape that exists in U for all x, AD. And this is a recursive translation until you get into an AD that's quantifier free. So the whole idea here is that this time I didn't even touch it. Oh gosh.
You want me to get Tomasz?
So he said that we might be able to put the slides on the machine here.
Do what?
Like there's a computer, and he was saying that we might be able to put the slides on the table.
I have no idea what you're talking about, Joseph, please. I think it's just this, perhaps there's some malcontact here or something like that. Otherwise, I don't know. I'll be touching this thing to see if it's malcontact. If not, we'll see how it goes. So the idea then is to kind of transform any formula into a formula of that shape, and with that, what you need to do is to be as constructive as possible, while being able to interpret all of classical piano arithmetic, which is the suggestion of Professor Truster, who I'm showing the picture up there. And the original dialectic interpretation then appeared in the journal Dialectica in 1958. So that's this business of being as constructive as possible. Is that Gödel thought that functionals were much more concrete in his mind than the ideas of Heiting, of a function, a generic function that you use to produce something else. But and so I was saying the only thing that appears in the Dialectica paper itself is this translation as I'm repeating it there, and you can see that that for conjunctions, it does the obvious thing, just kind of distribute the conjunction between the two guys. The disjunction, it does the traditional constructive trick of saying, if it's 0, you go to the first coordinate, and if it's 1 or not 0, you go to the second. But the point is really what it does in the implication. And I hope, yes, and I'll kind of do this and come back, because this is the closer explanation of why the implication works the way it is. Because what you want to do is you want to start with there exists an U for all x, and there exists a V for all y, and you want to push these things in such a way that you end up with an exist and a for all. And you can do this pushing off quantifiers to the front, but the first one and the third one are totally constructive, but the second one requires independence of premise, which is something that is not valid constructively, and the fourth one requires Markov principle, which is only valid for the Russian constructivists, and the fifth one requires some kind of limited use of the axiom of choice. So this, as I was saying, is Spector's explanation of why this functional, so this exists V here, is a function simply of the U. So an F from U to V gives you an existential V here, and a capital F from U and Y into X gives you this capital X here. So back to what I was saying, the most complicated clause of the translation is the definition of the implication connective. And what we will do is that we will try to think of this stuff purely categorically. We're going to try to kind of think of that internally and purely categorically. And the logical intuition for people who appreciate thinking about the logic at the same time as the category theory is that these two functionals have a very different job to do. The little f, which simply takes U's to V's, it's like a realizability interpretation. It's just what, I mean, if you think about modified realizability, that's what the little f does. It takes a witnesses for the hypothesis and assigns to it a functional f, so kind of gives your witness f of u in the conclusion of the implication. But the interesting thing, the thing that makes Gödel's functional interpretation so different is what it does to counterexamples. So it takes a counterexample y to the conclusion b and pushes it back using this capital functional f here into the a. So it kind of, from a counterexample to the conclusion, you should be able to find a counterexample to the hypothesis. And you can read all about that and all the explanations of Professor Truster on the collected works. Okay, so this was the bit about logic. Now I want to move on to category theory. And I know that in this audience I don't need to explain much about categorical proof theory as being a version of Curry-Howard on steroids, meaning a version of Curry-Howard that instead of simply connecting programs to proofs, we also connect category theory. But that's what we're going to be doing. So types are going to be objects in an appropriate category. Terms or programs are proofs in the category. And the logical constructors are appropriate categorical constructions. And the operative word here is appropriate, because we can do it very easily for simply typed lambda calculus, but then we want to extend it to different logical systems. And one thing that people sometimes don't say, but particularly this year, it's important to say, is that one of the things that makes this triangle work so well is that reduction of the lambda terms is proof normalization, which is due to Tate, who sadly left us early this year. And the good point about this whole thing is that we can then transfer results and tools from logic to category theory and to computer science as much. So the whole point of that is that we can solve the problem in either of these three vertices and then push the solutions to the other sides. Okay, so just pictures for you to think about. I mean, I hope everyone recognizes everyone here. And now we're going to get to looking at the category theory behind Gödel's dialectical interpretation. So Martin Hyland, who was my supervisor, suggested that to provide a categorical model of the dialectica, we just look at those two functionals that we discussed a minute ago. So a little f going from u to v, and a capital F going from u cross y back into x. And I looked very much and tried to find a Cartesian closed category, because, as I was saying, Gödel was trying to be as constructive as possible, and if the category theory is working well, then it should give us a Cartesian closed category. But I couldn't find a Cartesian closed category, no money or love. So I kind of came to Martin complaining that life was hard, and instead of saying to me, oh, that's because you're stupid, he said, oh, so Girard's been talking about this stuff. So maybe what? And I said, okay, I can prove a monoidal closed one, a monoidal closed category. And so he said, okay, maybe that's because we are dealing with models of linear logic. And that was very good, because this is a long time ago, and at that stage, linear logic was not as kind of important as it is now. So it was very good for Girard to say that Gödel had thought of something that could be construed as linear logic, and it was very good for me because I was one of the first people doing models of linear logic. And my models are particularly nice, as you're going to see in a minute. So that's Jean-Yves Girard, and I hope everyone knows that the basic idea of linear logic is that assumptions cannot be discarded or duplicated, they must be used exactly once. And there were other approaches at accounting for logical resources before, but none of the other approaches had this ability that linear logic has of accounting for resources when you want to, and otherwise falling back in traditional logic, given the famous Girard interpretation that transforms a normal implication into a linear implication with a bank. So what I wanted to show you is how we do these things in the categories, right? So I kind of thought I'd better remind you that when you have modus ponens, you can have A implies B, you have B, and A implies B, you have A and B, because you can just project the A and you've got the B by modus ponens, so you can reuse your A. But when you have a linear implication, you cannot do the same. You can use some sort of modus ponens or evaluation to produce the B, but you cannot reuse when you do that, you use up your A. It's a bit like a dollar bill, so you can't use it again to produce this A, so you cannot reuse the A. And the way that, so that means that you have two different conjunctions, a traditional conjunction where you can discard, and a linear conjunction where you cannot discard the B. And the way to go back to normal logic is this operator that Girard called the of course, but people mostly call bang nowadays. And once you have the bang, then you can reuse it, and you can discard things that have a bang on them. Okay, and how does that happen in the category theory? Well, it's kind of doing the traditional things. It's very easy because you just use Cartesian products or real products, and you really use functions from A to B. You just use what's called an exponential in category theory. The names are complicated because Girard calls the bang operator an exponential, whereas category theory is called this thing, the set of all functions from A to B, an exponential. And so we just have to be careful about when you use exponential or not. But the fact is that the real Cartesian products have projections and diagonals, so it's not linear. So you need to use tensor products and internal homes in category theory. And this was very easy, and everyone in category theory knew how to do that since the 60s. Knew how to do tensor products and internal homes in category theory, but what people did not know much was how to define the operator bank to make things back to normal. And so what happened to my category, the category that I was trying to define, was that Martin had said, start with a category C, that's Cartesian closed, and we think about the other properties that it has in a little while, but build a new category. And the objects of this new category are relations in C. So they are monics into the product U cross X. And you can call them triples because you probably want to remember what was the domain of your relation and what was the codomain of your relation. And so, a relation, kind of, if you're thinking in sets, just means that either U alphas X or it does not. But when you're trying to do that categorically, you have several different ways of saying the same thing. One of them is using monics, that means sub-objects. Another one is to actually making maps into the object 2. So that's another way of writing a relation, is to say U cross X goes to 2, and that's my alpha. This is kind of important because, guys, we are trying to think about how to formalize this stuff. So, the different ways of doing things mathematically might end up being very important when you do the formalization. So, okay, so the objects are easy. We just kind of think about relations, either using sub-objects, as I'm doing here, or using kind of maps into 2. So this 2 here, you guys know, right, what I mean? I mean, 0 plus 0 and 1, that's false and true. And so that's why I was saying either U axis or it doesn't. Oops, going to the wrong direction. So either U alpha axis or it doesn't. But so the important thing is the maps. And hence, now I'm going to write my objects as U x alpha and V y beta. And the morphisms, the things that are supposed to internalize implication in the dialectica, are pairs of maps, little f from U to V, capital F from U cross Y, back into X. And here comes the exciting bit, such that a semi-adjunction condition is satisfied. So the semi-adjunction condition is that if you take a little u and u and a little y and y, then u alphas f of uy implies f of u beta y's. So this, again, is not very traditional in category theory. In category theory, when you have triples like that, you normally think that things go mapping this way, and this way. Kind of, this one goes down, up, and down. So it's a little different. And so the theorem was that many years ago that the category DC has a symmetric monodal closed structure. It also has products and weak co-products, and that makes it a model of modality-free intuitionistic linear logic. And this is what I've been trying to convince people here to formalize. Yes, Claudio?
Just a quick question. So before you provided the intuition of U and X as example, a counterexample, the relation, do you have one sentence intuition of what is the relation alpha?
Sorry, say it again.
The relation alpha between the U and X.
Yeah.
Do you have one sentence intuition about it?
Well, they are just kind of, I mean, the intuition is just that they are the types of the quantifiers. That's nothing very much more than I can say. I'm going to say something else in a minute. Kind of, I'll give you some examples which might help a little bit. But so the theorem here is just that the data above does provide a category, And that means you have to show what are the identities, and the identity is just the identity in the first coordinate and the second projection in the second coordinate. And here's someone who's asking about, who's thinking about lenses. Here you see why I say this is like lenses, because the composition of these things is just simple composition on the first coordinate, do F and then do G, but on the second coordinate, you have a very complicated composition that is exactly the composition of lenses. You first you have to duplicate your U, then you apply the first forward map on the middle U, then you do the backwards of the second map, and then you do the backwards of the first map. And this is the composition that people use in lens, and when they first look at it, they go, I don't like this, but then they it's very useful for lots of things. There's lots of libraries of this stuff, because this sort of mapping is important. And of course, you see, these things, I didn't even have these things written on my slides for mathematicians, because this is a triviality, mathematically speaking, right? The fact that these things do make a category, was because I create them to make a category. So associativity and unity laws come from the base category, and the only thing I have to check is the semi-adjunction, that condition on the implication works for these guys. So this is totally trivial, and I only wrote it down more carefully this time because I was trying to do the formalization with people visiting here. But okay, first of all, a little bit of intuition, and the intuition comes from Andreas Blass. So the intuition is this idea that instead of thinking of them as formula in Heyting arithmetic, you could think of them as problems in computational complexity, if you like to think about problems in computational complexity. So one object like that can be seen as representing a problem, and the U guys are instances of the problem, while the elements of X are possible answers to the problem. And the relation is only going to say if the answer is correct or not. So this is something that Andreas Blass said in 1993. He looked at the stuff that I was doing and said, oh, you should think about like that. And that explains some of the applications in set theory and in Kolmogorov's theory of problems from 1932. So you can push these things back quite a bit. And so examples here, totally trivial examples, are something like if you take the object natural numbers, where the relation is simply, the relation is simply that we say they are related if they are exactly the same. It's a very trivial sort of relation. You can have a more complicated relation. So instead of taking n and n, if you take all the functions from n to n, which some constructivists would go berserk, right? But you take as the second component to just n, and you say that a function f here is related to a single element here. If applying the function to the functional gives you the same thing. And I put the two things about, I put real numbers here as well, because we're thinking classically, so everything goes. You can do Lifshitz functions, you can do whatever sort of stuff you want. But oh yeah, I see. I moved a little bit the order on the things, because having this thing that is a category is then very easy to find a tensor product in it. And the tensor product is just what you'd expect. You have one object like that and another object like that. So if you want a product, what you do? Well, you multiply the first two coordinates, you multiply the second two coordinates, and you multiply the relations. And that, lovely enough, will give you a bifunctor and with a unity, which is just a terminal object in each one of the coordinates. So we have this proposition that the category DC is a symmetric monoidal category of this tensor and unity. But you see, here's the point that I got so desperate trying to tell Martin that this thing did not work. Because this thing looks like a lovely tensor product, but it's not a real product. You cannot, there are no projections in this stuff. if you take a pencil like that and try to project it to have just the first coordinate, you project without any problems in first coordinate. But from x, you cannot get back into x cross y because you don't know any y to go to. So this does not work as a projection. And you also do not have diagonal functions, because if you take a new x, y, you can simply go to u cross u, you duplicate your u, but you take two things here, and they don't have to be the same. So you have an x and x prime, and you need to get back to x. What do? You could throw one way, or throw the other one way, or you could try to smash them together, but naturally, there's nothing that you can do. I'm lying a little bit. The recursion theorists have a way to kind of make a function going back here, but it's not very categorical. It's not very lovely like the rest of category theory. It's kind of using funny negations. So finally, back to here 2 weeks ago. Can we formalize this construction? Sure. In 2016, I was already trying to formalize this construction. And I had another formalization with someone called Harley III, who is a professor in Augustum. And the reason why we did that formalization was for a very specific need. We wanted to show cut elimination for a system called full intuitionistic linear logic. And I have to confess that, Harley did the formalization, kind of showed me that everything worked for proving the cut elimination, and I didn't even read the file well enough to notice that he had no relations. So he just used the types of the morphisms to prove. And for proving cut elimination, that's hunky-dory, no problem, because either there is a map or there isn't a map. And if there is a map, we are home and dry. Then in 2022, Eric Bond came to work with me, and he wanted to do a different formalization, and he wanted to do a generalization. He wanted dependent types. And then the mathematics wasn't in place, and there was not enough time, so nothing much happened to that. Then I kind of came here and met Reed, and he said, oh, we can do that in cubical actum. And I was very excited about it, but then he left before we did anything. Then Max here kind of said, oh no, okay, let's do kind of act. And then he looked and said, no, let's do shoe construction. The dialectic is a bit too problematic with this semi-adjunction condition that I was showing you guys before. So now I'm pinning my hopes on Mario, who kind of already has proved in Lean the propositions 1 and 2 that I just described. But that's hopes, because the internal home, which is the hard one, is not done quite yet. And yes, I'm not the first mathematician to say that, but it is amazing how hard it is to transform informal mathematics into the stuff that the computer kind of can see.
Very difficult to see where the bottlenecks are.
The problem...
Because mostly it looks like a bunch of definitions, but...
Looks so not normal and decent definitions, right?
Proofs that essentially involve just a bunch of manipulation.
Yeah.
So is there something where the definitional mechanism is inadequate, or is it that the proofs are actually non-trivial?
Well, Max is here. He can explain to you why he thinks that doesn't work. But the reason it's kind of problematic is that we have loads of pullbacks. I'm showing the definition for humans, right? So I'm using the internal language to say this relation implies this other relation. And the way that we actually, even I formalize it in my thesis, is using 2 pullbacks and a relation between the 2 pullbacks, saying that pullback number 1 is smaller than the other pullback, so there's a unique map over there. And when we do that, that looks very big, even only just doing the associativity. So the associativity kind of already causes an awful lot of trouble because you have to do it with that very strange composition. So you have pullbacks that you have to glue together with, do you remember this composition here? So you have to glue pullbacks along this stuff to make sure that the relations are preserved, that they work. And you know, so far so good. We managed to do that for associativity, but now what we need to do is do that for things like that. We need to define this relation that's beta to the alpha. So we need to get a sub-object of this product here that internalizes the definition of implication. So it needs to be the biggest thing such that alpha and this thing are less than equal to beta. So what you need is to, I mean, I had never realized this before, but I should have. What you're doing is you're kind of thinking of the sub-objects of any object in a category C, and for those sub-objects, what you know how to do is you know that they have an order, and you know that you can do meet of them because you can just do the pullback of one against the other, and you know that you have a top because the category C is Cartesian closed, so there is a top there. But then you have to take a meet semilattice and say there is an implication, a heighting implication there. And I'm pretty sure that this is somewhere in any of the books from kind of the books in order theory. They must have that. But I don't remember how to prove that there is an implication there. And that's where at least I am stopped. And I do not know what Mario is doing, but that's where I'm having problems is, I mean, I kind of this morning I got myself vaguely relieved because I kind of found a paper of Peter Fried saying, talking about heighting semilattices theory and showing that a collection of results about heighting semilattices, which is exactly what I have here, right? But you know, he doesn't have to, he's assuming that this thing is a heighting semilattice. What I need to do is prove that these guys are a heighting semilattice. So, you know.
That is column came up for his like master's thesis or something.
Who?
His column.
You should, I don't know, probably. I mean, I don't think it's impossible. I just kind of never thought about that along these lines.
40 years before Heidi.
Cool. Okay, so that's what we need to do, and we can discuss it very much. And as I say, for humans, it's perfectly easy. You just create the object there and show that it's a bifunctor, which I'm told in linear you call whiskering, kind of because you have to put one map to one side and on the other side. I do not know if it's a problem that the first coordinate is contravariant. And then we prove the most important thing, which is I always say to my logician friends that this is just what modus ponens is about, right? Because it's A and B proves C, if and only if A proves that B implies C. So it's the adjunction. And then the rest is okay. We do products and actually not co-products, weak co-product. And this turns out to be very important later on because you don't have real co-products here, and when you do that in the containers and in the lenses, they are real co-products. So that's a mismatch between the two structures. And so you prove the first theorem of the thesis, which is that the category DC has a symmetric monoidal closed structure and products and weak co-products, and that's a model of exponential-free intuitionistic linear logic. And then you get to what I thought was the most exciting part, Sorry, is that a question?
Yeah.
Oh, cool, sorry, you can just stop me.
Okay, sure. The previous theorem, earlier you referred to a modality-free interactionistic theorem. Do you mean the same thing by exponential? Because the exponential.
That's right. I'm so sorry. This is me mixing up the category theorist notation to the logical notation. So
Okay,
exponential free, I mean without bang.
Yeah, and that is the modality that you were talking about earlier.
That's the modality, correct. Sorry. And so I'm not going to give you the full story here because we are getting late, but as I was saying early on, the important thing about linear logic is to have a bang so that you can go back and have normal logic as well as the resource careful logic. And that means that you have to have this operator and the things that you know about them is that, you know, bang of A has to duplicate the bang A. The bang of A should be able to erase it, kind of going to the identity for the tensor, and that one we have, we are good. And then there's this other two rules for the bang A. One is that you can always go back to A, and the other one is that you can go what some people call jigging or promotion, because you can always bang A, it goes to bang bang A. And of course, because we are doing category theory, you want this to be a functor. So you want to give in any map of this shape between A and B, then you want to be able to apply the functor to it and get something like that. And the thing that's very beautiful about this work is that there is an obvious way of finding a bang that does all that you want. And this beautiful way is just kind of down here. You know, you take an object like that, you kind of keep the U the same way as it was, and you just take the free commutative monoid on X. And if you take, so you know, you think about this as kind of sequences, X1, X2, X3, or empty sequence, or all the ones kind of are finite ones. And this then behaves as a co-free comonoid. So this is a very special model of linear logic that actually Lafont kind of said should exist many years ago, but no one could find one to begin with, and the dialectics provide that. But that's a pain in the neck. You have to do lots more of calculations, and I'm not going to even, I mean, since we are still stopped on is a category and has a tensor, I'm not going to even try to think about these things. But you know, I just kind of wrote this one to show that what you need for bang is a little bit of a beautiful thing. So there's a more modern way of thinking about that, which is to say that there is a monoidal junction between the category that you're thinking of and its co-free, co-Kleisler category. But this model satisfies all the definitions of existence of bang that you might want. And once you get all these things in place, you just kind of, it's ducks in a row. You just shoot them and you get the theorem that you want, which says that the category, the co-Kleisler category associated with the comonad is Cartesian closed. It's one-line proof. Everything works. Kind of when Girard saw that in Boulder in 1987, he said something like, no, you don't want to do intuitionistic linear logic, you want to do classical linear logic. So simplify the stuff. And instead of having that map that I said was so exciting because people keep rediscovering it in computer science, he said, well, just forget about the U here, just take maps that are more traditional in category theory. So U goes to V and Y goes to X, but keep the condition, or keep the version of the condition simplified. And this is the second half of the thesis, and it's kind of gives you again a symmetric monoidal closed structure. This time we have products and normal co-products. So we have a model of CLL or field without modalities, and then you put a modality in and you get everything that you wanted. But to my mind, this is not as pretty as the first bit, because the first bit, you started from the notion of modeling something that that's a very arcane bit of proof theory, the dialectica, and you kind of provided the model, and when you provided the model, you discover that the model is also a model of linear logic. So it's it's a double whammy. You started from something and you get two models for the price of one. Whereas here, I have never been able to make sense of, to make proper category theory of what Girard said, that this thing should be hanging quantifiers. Maybe it's because I haven't tried enough to think about hanging quantifiers. But, so it's not as exciting as the previous one, to me, at least so far. And then, you have to go through the whole thing again. I think I never go forward. Yeah, so you have a tensor. And the other thing is that we simplified the internal home, but now the tensor becomes much harder to do. It's a cross product, which is complicated. And if it was a bit earlier, it was kind of, actually, let's kind of just do this for fun, because, I wanted to show you in the simplified version how you think about modus ponens categorically, right? And how the types are doing all the work for you. So if you think that you have, well, it's a little bit funny because I kind of doing the complicated tensor on this side, so the cross product here. But what I'm just saying is that you have a function here and you have two functions here, right? G1 going from Z to X to the V, and G2 going from Z to Y to the U. And what you do is just kind of currying and uncurrying things. So if you have a little f from U cross V to W, you can simply send the V to the other side and end up with U going to W to the V. And if you have a G2 going from Z to Y to the Z, you can just carry it twice to get, carry it twice to get this one here, because you get U cross Z into Y, and then send it again, you get U to Y to the Z. So the types just work perfectly. You don't have to do anything. They just fit. I should have put the G2 hat here, but it's because I have to do two currings on that one, so that I can curry it twice. So that's it. So you have this category, which is a model and everything. And you have a bag operator, but again, the bag operator here is a real pain in the neck, and because it's a composite of two different comonads, and each one of them is plenty of work. So you end up on where you want it to be, that there's a monoidal junction between this GC and its co-Kleisli category for this composite comonad bang above, and you see what the new comonad is doing. It's doing the same that it was doing before, X to the star, but it's also taking function spaces into it, so complicated. So, conclusions. I introduce you to what I think is an underappreciated dialectica models for linear logic, DC and GC. DC was the first mathematical co-free model of linear logic, and the first one that kept all the distinctions that Girard wanted to make. Both of them, GC satisfies the mixed rule, so some people might think that's not so nice because of that. And I kind of very much try to hint at the importance of interdisciplinarity. We want to do category theory, we want to do proofs, and we want to do programs all at the same time. But much more work is needed for applications, and in particular, there is some applications using games that I haven't even started talking about. And that's kind of it, really. So I think when I kind of wrote this slide, it's a very old slide again, I kind of wrote here that working in interdisciplinary areas is hard but rewarding, and that this is a very fun place to be, kind of between logic, computing, linguistics, and categories. But so I kind of wrote about barriers being unwillingness to waste time on formalizations, and I did not mean formalizations in the sense that we're talking about here. I meant just the fact that when people think about phenomena in computer science, sometimes they think that it's a waste of time to formalize the phenomena, to kind of transform the phenomena, the tricks of the trade that they use all the time into science, into proper theorems and theory. I don't think it is. I think that is one of the barriers for our kind of flourishing, is the fact that some people think it's a waste. But of course, they are kind of good enablers too. So we have international scientific communities, open access, open source software. And I hope growing interaction between fields, which is what we're trying to do here and now, right? And now that's it. Thank you.